In the realm of classical mechanics and the microscopic constituents of matter, there exists a fundamental discipline known as particle mechanics, a branch that focuses on understanding the motion and behavior of particles. This narrative, woven with principles from classical physics, Newtonian mechanics, and the dynamics of individual particles, unfolds the story of motion, forces, and the timeless laws that govern the behavior of particles in isolation or in interaction. Newton's laws of motion. At the heart of particle mechanics lie Newton's laws of motion, the timeless principles formulated by Sir Isaac Newton in the 17th century. These laws provide the foundation for understanding the motion of particles. The first law states that an object at rest will remain at rest, and an object in motion will continue in motion unless acted upon by a net external force. The second law links force, mass, and acceleration, while the third law asserts that for every action, there is an equal and opposite reaction. Kinematics. Particle mechanics embarks on a journey into kinematics, the branch that describes the motion of particles without consideration of the forces involved. Concepts such as displacement, velocity, and acceleration become the tools to characterize the trajectory and dynamics of particles in motion. Dynamics and force analysis. The narrative deepens with dynamics, where particle mechanics explores the forces acting on particles and their effects. The fundamental equation, derived from Newton's second law, reveals the relationship between force, mass, and acceleration. Force analysis becomes a pivotal aspect, unraveling the influences that shape the motion of particles. Projectile motion and circular motion. Particle mechanics unfolds the intricate patterns of motion, including projectile motion and circular motion. The principles of physics govern the trajectory of particles launched into the air or moving in circular paths. The interplay of gravitational forces, centripetal forces, and inertia becomes central to understanding these dynamic scenarios. Energy and work. Particle mechanics introduces the concepts of energy and work, offering an alternative perspective on particle dynamics. The conservation of mechanical energy becomes a guiding principle, providing insights into how the total energy of a particle system remains constant in the absence of non-conservative forces. Collisions and impulse. The discipline delves into the physics of collisions, where particles interact through forces over a short period. Impulse, a key concept in particle mechanics, relates the change in momentum to the force applied during a collision, shedding light on how interactions between particles can alter their motion. Applications in engineering and technology. Particle mechanics finds practical applications in engineering and technology. The principles of motion, forces, and dynamics form the backbone of designing structures, analyzing the motion of vehicles, and understanding the behavior of particles in industrial processes. Quantum mechanics connection. While particle mechanics primarily operates in the classical realm, it serves as a precursor to the quantum realm. As the scale decreases to the microscopic, particle mechanics lays the groundwork for the transition to quantum mechanics, where the classical laws undergo profound transformations. Statistical mechanics and thermodynamics. Particle mechanics extends its reach to the macroscopic scale through statistical mechanics and thermodynamics. The behavior of particles at the microscopic level contributes to the understanding of macroscopic properties, heat transfer, and the principles of thermodynamics. Astrophysical applications. Particle mechanics extends its influence to astrophysics, where the motion and interactions of celestial bodies are governed by the same principles. From the dynamics of planets in the solar system to the collision of galaxies, particle mechanics provides a universal language for understanding cosmic phenomena. In essence, particle mechanics is the foundational melody that resonates through the classical physics of individual particles. It is the discipline that, through the lens of Newtonian principles, uncovers the intricate dance of particles in response to forces and influences. In the grand theater of classical mechanics, particle mechanics stands as the timeless conductor, guiding the exploration of motion, forces, and the fundamental laws that govern the behavior of particles in the vast tapestry of the physical world.